Greetings, everyone. Not in the shed today because we're having a bit of a cold snap in Ireland. It's getting down to -3 degrees Celsius. I hear people in North America and Canada going, "Oh, yeah, that's not really cold." And you'd be right, but but still, the shed's it's the little heater struggling to keep it warm, and it's hard to do stuff with cold fingers, even if they are only getting down to even if it is only -3. So I'm in the kitchen. So, bosh, nice cooker. Anyway, I wanted to talk about remote controls. This is a cheap little remote control I got from Deals, which is kind of a pound, what people in the UK would call a pound shop, or people in America would call a dollar shop, except everything costs not a euro, €1.49. It's a universal remote control that can control up to 10 devices. So is it 10 devices? Yeah, 10 in one. So I'm not quite sure. I haven't actually figured that bit out. There's 8 buttons, but it says 10. 10 in one. Never mind. It was $1.49, and it's pretty amazing because I remember when universal remotes first came out in the late 80s, early 90s. They're quite expensive. Like, I remember there was a brand in the UK and Ireland called One for All, and they had various levels of luxury device. So the very basic one could do channel up, channel down, volume up, volume down, and a power button. That was it, 5 buttons, and they were like £20. I was living in the UK at the time, and they were £20. And if you wanted something that had more buttons, 30, 40, 50 quid. And I think they actually had one that went up to 100. And then you've got like the ones that are used by home cinema, home theatre enthusiasts with fancy touch screens that nowadays run the likes of Android or Windows CE or Windows Phone operating system, and they're like freakishly expensive, like 500-600 quid upwards. But if you're into that kind of thing, then yeah, you can spend your money any way you choose. Anyway, so for $1.50, it's a pretty amazing piece. It was pretty amazing that they've actually got this much functionality into it for that price. It's the kind of thing I like to show how far technology has progressed, because you go to a pound shop and they might have like iPhone leads or iPad leads or lightning connectors, HDMI leads, and toys for this, for a set price, and you think, oh, that's impressive. But then you look at this. This isn't just something you knock together cheaply. Someone has to go out and research the codes for the televisions. Someone has to build some sort of microcontroller and program it. Someone then has to build the hardware, which, even though it's really cheap hardware, it still does the job. It works, and it works fairly reliably. And to get that sort of produced for the cost of $1.49 is pretty amazing, to be honest with you. So let's have a quick look at it. So here it is. I've actually already opened it. That's the reason why it opens so easily. Anyway, CE probably means China export, because a little interesting fact about the CE symbol, it actually officially means Conformité Européenne. Pardon my French, but it's a self-certifying standard in Europe to say that you conform to European standards. Now, the official CE, if you were to continue round the C and turn it into a circle, the right hand side of the circle would intersect here with the E, with the line in the E intersects with a semicircle. If they're closer together, it's not the official CE symbol. And if you go off to Wikipedia and look up CE, it actually says that there's an unofficial designation, China export. And probably what that means here. Anyway, build quality, yeah, it flexes. It's cheap plastic. You can see the injection molding wasn't done very well. It's no okay, but what do you expect for $1.49? The buttons, they're nice. They don't feel horrible. No, you can feel around and find them in the dark. It does what you want to do. It takes two AAA batteries. I have actually tested this with a couple of devices that I have, and it works fine. No, it does the basics: channel up, channel down, whatever. It doesn't have the coloured buttons you usually find on a lot of UK and Irish television remotes or European remotes. That was from what was known as the fast text teletext service, where you'd coloured links at the bottom of your teletext page to jump to specific pages quickly. Since the development of digital TV, that system has been taken modified the colours have been modified to control interactive television applications, such as the BBC's interactive text service that they have on their digital platforms. And as we call it here, Airtel, digital Airtel, which is a bit of a misnomer because the original teletext system was still digital, albeit delivered along analog radio waves. I'm rambling now. So let's just open it up. I'm assuming... Actually, before I open it, I want to show you the surprisingly decent remote instructions for such a device. No, the text's a bit small, but it actually explains it all pretty well. No, a lot of the time the language they use in these instruction sheets is just incomprehensible. So you're like, it hasn't been very well translated. But the code list is huge. Like, I've actually bought brand name universal remotes that come with like the codes for maybe 20 or 30 brand names. This has pretty much everything I can think of. It does miss out one or two fairly recent brands. Like, it doesn't have hands-free, which is, our television is a hands-free. Interesting fact for you, if you've bought a Philips TV in the last few years, you didn't actually buy a Philips TV. Philips don't make their TVs anymore. They sold the rights to make Philips TVs to a company called HandsG, which makes hands-free TVs in Hong Kong. So there you go, just a little interesting fact for you there. Kind of worry about Philips. They're a company that just keeps selling bits off, and what was once one of the world's biggest electrical conglomerates is now basically medical equipment, light bulbs and kettles. But anyway, there you go. It's a pity. If you're ever in Eindhoven in the 80s or the 70s, you probably would have visited the Evoluon, which is one of the most amazing science exhibitions that has ever existed, inside a big building that looks like a giant mushroom or a spaceship. Now it's a conference centre. It was shut down in the late 80s, which is a pity. But anyway, Philips created it, and it was fantastically amazing. It was fantastic. I went there in '88 and I loved it. Anyway, I'm going to rip this thing open because there's no screws. Hopefully I won't put the screwdriver through my hand. Oh, I broke something there. Ah, well. Let's see what we have here. Oh. As I expected, it's a sort of a custom chip covered in a blob. Dear, dear, dear. Right. So there's the contact side of the circuit boards. If you don't know how they work, you've got little interlocking contacts, like kind of the interlock like that, but there's a separation between them. On the back of the buttons, the rubber chiclets, I think is what you call it, there's a little bit of carbon there, and when that presses down onto the contacts, it short circuits them, and that's what registers the button press. Yes, I'm actually a little bit disappointed. I wanted to be able to show you a chip name, but look at it. Look how simple the construction is. Like, if you were to look at if you were to take a standard manufacturer's TV remote, say a Philips or a Sony or any sort of reputable manufacturer, and opened up the remote, you would see a lot more going on. There would be a hell of a lot more going on here. There'd be chips, there'd be a lot more discrete components such as capacitors and resistors. This is amazingly basic. I'm going to see if I can pull this off. I don't think I'm going to be able to do this, so I don't want to put the knife in my hand again. I've done that in the past and that's not very pleasant. Nah, that's not going anywhere. So yeah, not as interesting as I'd hoped it would be, to be honest with you. I'm sorry. But what I will say is, to produce a working universal remote control that can control 8 or 10 devices and sell it for €1.49 or £1 in the UK is amazing. Even leaving aside the hardware side of it, to actually have someone who is willing to go out and do the research to get the codes to produce this document and then program him into the whatever chip is underneath this epoxy blob here, and then test it to a point where deals or whatever retailer is willing to buy how many hundred thousands of them, safe in the knowledge that they're all going to work and they're not going to be returned. Well, you'd return something that costs $150, I don't know, but I'm sure some people would. It's amazing to show how far technology has come. No, it is really amazing. So anyway, what I'm going to actually do is quickly give you a bit of a lesson in how remote controls actually work. You might find this interesting, you might not. So I need a pen, clear away the rubbish, and a sheet. Now, a remote control, infrared remote control, has a little infrared LED in the front of it. And it's very simple how it works. It switches on and off, but it can switch on and off very fast. So it sends out a series of pulses. In the television or the receiver or whatever device is receiving the signal, there's a little infrared sensor. It's attuned to the actual frequency wavelength of the color of the infrared diode. So like infrared spectrum's can be fairly wide. So it'll sort of have a filter on, it'll tune it into a specific wavelength of light that's being emitted from the LED in the remote. And it basically is looking for flashes and a certain number of flashes per time period. So let's say, for example, a common protocol that is used a lot, or was used a lot, was RC5, which was developed by Philips and became adopted by manufacturers all over the place. There's also the NEC protocol, which is used by a lot of Japanese and Far Eastern manufacturers, but they're very similar in operation. So what happens is that the television looks for a series of flashes. In the case of the RC5 protocol, it looks for 38 pulses in the space of 25 milliseconds. So I'm not going to do the maths to break down it specifically, but let's just say that you're looking for 38 very fast pulses very quickly. And that indicates a signal is being transmitted. But you need to send out multiple signals. So in the remote control itself, it sends it out as a 5-bit signal with start and end bits allotted on. So I'll simplify it a bit. So let's just say number 1 is the power button. So 0, 1, power. Number 2 could be volume up. And number 3, volume down. And this could go up to, and if you've got a 5-bit address space, it can go up to 64. So you would write out a list of numbers to say that 11 might represent digit 1. 12 might represent digit 2. Oh, it doesn't matter how it's up to you how you implement it, and up to the TV to understand what each number means. But what matters is how it's transmitted. So the package that will be sent out would start off with a 1. It's always a 1. That's to alert the receiver that a signal is being sent. And then it follows on with the 5-bit code. So let's take number 1 as power. So 5 bits in binary for 1 would be that. And then there would be a package at the end. So let's say a 0, 1 at the end, which is again up to the manufacturers how they implement that. Generally you want to finish with a 1 or a 1, so it's easily identifiable. Now the problem is, actually I tell you, this symbol here in the Philips RC5 protocol, I believe, and I'm willing to stand corrected on this, is a flip bit. So although you can only have up to 65 codes, if you've got more buttons on the remote, you can set that to 1, and that effectively restarts this at 66 upwards. So you can have 128 buttons on the remote, but we'll ignore that for now. So the problem is when you're transmitting a signal between two devices, you want an ideal situation to have matched clocks. So take your Ethernet, for example, your wireless internet or your wired Ethernet. The card in your computer and the card at the router will have a clock chip on it, which generates a time signal. And what it knows is that each packet of data is sent every, say, 1/1000th of a second. It's actually quicker than that, but let's just say every 1000th of a second, a single piece of data is sent. So it's synchronized. So let's say you wanted to send 100110 over the network. This is at a hardware level, and the signals were sitting. The clock rate was 1 every 1/1000th of a second. So what you would do is you would sort of say you would break it down to gaps like this here. So each gap is 1/1000th of a second, 1 millisecond, and so on and so on. And you'd have your 0 volts, which is nothing, and a logical 0 would be sent at between 1 and 2 volts. So let's say 1 2, 3, 4, for example. So 1 will be sent out as something between 3 and 4, so it will go there. And then a 0 would be sent out here, so you'd send 2 lines here and here. A signal would be sent out for 2 milliseconds at between, say, 1.5 millivolts. And then when it jumps up to 1 again, it would go back up to here and here. Now, the problem with this is, so this goes here, this here, this here, this here, this here, here. The problem is, what if you're dealing with two devices that can't synchronize their clocks? So, for example, in this case here, if the clocks are misaligned, how does that know the receiving device could misinterpret that as a single 0, or maybe 3 zeros or 4 zeros. You just don't know if the clocks are right. And that's the problem with remote controls, is they don't have a clock in it, and it would be expensive to put one in, to design them, and also the fact running off a battery, as the battery runs down, it would affect the clock accuracy. So what you use is a system called Manchester code. And Manchester code dates back to the Manchester Baby, which is the world's first stored program computer, which I believe was created in 1946 in the University of Manchester. What Manchester code does is it self-clocks a bit stream. So let's say you want to send 10011. For each individual bit, you send 2 signals. So in the case of, and what you identify whether it's a 1 or a 0 by whether the signal goes from 0 to 1 or 1 to 0. So from, let's say for example, you wanted to do a 1. A 1 would always be a peak followed by a trough. So that would be, going back to our voltages, if that's 0 and that's 1 there, 2, 3, 4. So that would be, the 1 would come as between 3 and 4. Followed by the 0, which would be a voltage between 1 and 2. The 0 would be like this. And another 0 would be like that. And the 1s would be like that, up, and like that. So you know that every 2 of these equals 1 bit. And you can do a bit of math. When you receive this signal, you can actually analyze the signal and to work out what the clock rate of the sending device was. So even if they were coming a second apart, or 1/10 of a second apart, you can easily identify the individual bits by whether they go from up to down or down to up. It takes up twice as much bandwidth because of course you're sending 2 signals for every bit. Oh, dog's barking, wonder why. But it works and it's fairly widely used. It's used in remote controls. It's actually used in RFID cards. So if you're paying for your bus using an RFID contactless card, because there's no clock in the actual RFID card, it would actually send its data out using Manchester encoding. So going back to the remote controls, how it applies there. Instead of sending out a voltage, let's get rid of this sheet. It's a voltage. It actually says a burst of 38 pulses is equal to a logical 1. And again, it issues 38 of these for every 25 milliseconds or thereabouts. So let's say you wanted to send this of 10000101. So what you would actually have is something like this. The LED would give out 38 pulses like that, and then nothing. For the 0, it would go nothing up 38 pulses. So that's why the 1 is important at the start. That kicks the process off, so the receiver in the television is expecting to see a burst of 38 pulses. And then it would then wait to see what comes next. And it would either expect next after this to receive that or that. And then it'll start buffering what's coming in, passing it to the IC circuit, which would then effectively try and decode it. So reducing this down in size a bit, because that's too big. So let's just start again. So this is the baseline, nothing's being transmitted. So 1 0 0 0 1 0 1. So 1 would come out 38 pulses nothing. 0 would be nothing, up 38 pulses. Same again, nothing, up 38 pulses. 0, again, up. 1 would be 38 pulses, nothing for the rest of the period. 0, nothing, up 38 pulses. And the 1 would be 38 pulses, done, nothing. So therefore, the circuitry in the TV would interpret that, work out what the bits are, and pass that on to the circuitry to look up what that number, their number encoded here means, and do that thing on the television. So if you pressed cent 0, 1, it would look up its internal tables and say, well, that means switch the TV off. So it would switch the TV on or off, depending on the standby state. The beauty of this is, as the batteries and television remote controls get a bit, as they run down, they will actually slow down what is sent. So there is in the ideal situation, it's 38 pulses per over 24.8 milliseconds, let's say 25. So here you're effectively talking 50 milliseconds between here and here. So that each individual bit takes 50 milliseconds, sorry, microseconds. Jeez, getting it all wrong. Microseconds, which is smaller still. So yeah, it's quite ingenious really how it works. It's simple, and as the batteries run down and it actually literally slows down the speed at which it's sending out, the TV can cope with that because the Manchester encoding lets it see what is being sent regardless of the clock speed. And as long as you've got something that identifies the start and the end, in this case sending a 1, and it expects 5 bits in between, which it derives the number from, everything is hunky-dory. Now in reality, the more modern remote controls use a much more sophisticated protocol. They would maybe send like, for example, the NEC protocol actually sends a device code at the start. So only certain devices will recognize that signal. So you could you'd fit in somewhere here a device code, and multiple devices could see the remote signal, but unless they recognize they're of that device code, they'll just ignore it. The Philips RC5 protocol, which is what I'm largely basing this talk on, was designed actually for one remote control would operate any CD player or any television that uses the RC5 protocol. So there's benefits and disadvantages. Now things are moving on. Like we've a cable television system called Horizon, which is a common all throughout Europe. It's not used in the UK. And the remote control for that is actually radio based. I don't know what the protocol is. I'm not prepared to take the remote control apart because it costs €45 to replace, and it appears to be it's not screwed down. It appears to be one of the ones, if you opened it up, you'd actually wreck it, and it's a fairly hefty piece of kit. And I'm assuming it's some sort of Bluetooth-like protocol. I don't think it is Bluetooth because the battery lasts a very, very long time, and you wouldn't have that with Bluetooth. But there's some sort of radio protocol that used there. So in the back of the days with infrared remote controls, if you lost the remote down the back of the cushion and you were pressing the button, it didn't affect the TV unless the TV could see the signal. With radio remotes, the TV goes haywire and you can't find the remote control because it's transmitting via radio. But anyway, so there you go. I hope you found that interesting. It's remote controls, very simple how they operate. They send out a series of high-speed pulses to the television. The television picks that up, and within those high-speed pulses is encoded Manchester code, which in turn can be translated into binary, which in turn can be then translated into a number that the TV understands. That video took longer than expected. I'm so sorry.